Our next speaker is Charmaine Thomas. Charmaine is a senior geologist geophysicist at GSWA and will tell us about the Perth Basin and basement and specifically new insights from deep-crustal reflection seismic profiles. Thanks, Charmaine.
Hi everyone, thank you for coming. So today I'll be talking about our current interpretation of the Perth Basin portion of the three new deep-crustal seismic lines that Fauna introduced earlier this morning. And first I'll give an overview of the basin geology, and then I'll touch briefly on the acquisition and processing, and then I'll also show examples of the seismic and show you how the new seismic has clarified structural relationships in the Perth Basin and how it's confirmed the depth and character of the basement. And I always like to start with this image here on the right, which is a relatable way for everyone to understand what the Perth Basin is. So it's a topographic image, and we see our familiar Darling Scarp there, which overlies the Darling Fault, and we have that deep ocean basin within the Indian Ocean there on the west, and of course the Perth Basin is in between. So here in Perth, we love our coast, we love our ocean, and we owe the existence of that ocean to the rifting and breakup of the supercontinent Gondwana that preceded it. The Perth Basin was the southern end of a narrow interior rift in eastern Gondwana, with the Yilgarn Craton to the east, so that's the area in pink, and India to the west. And it's now filled with Devonian or older to Cretaceous strata that are mostly confined to the west of the Darling Fault. The basement rocks to the Perth Basin are the terrains of the Proterozoic Pinjarra Orogen. And these terrains have varying lithologies and separate tectonothermal histories, despite their close proximity, which suggests their amalgamation along large structures that likely later influenced the development of the overlying Perth Basin. And you can see there our three seismic lines that we acquired are in black, and these are actually the first lines to image these Proterozoic terrains. So if you're not familiar with the active seismic method, it's very different to the passive seismic method you learned about earlier. It works very similar to other echolocation techniques like sonar. So first we need a means of generating acoustic waves, and that's what these are. These are vibrisized trucks. They have these large metal pads under their chassis that are lowered onto the ground surface, and they vibrate at controlled frequencies. And that acoustic energy travels down into the earth, gets reflected back off by rock boundaries across which there are strong enough contrasts in density and velocity. And any waves that are returning back to the surface get picked up by these geophones, they're seismic sensors. And that whole process, the time it takes for that process to occur can be used as a proxy for the depth to those rock boundaries. For these lines, the Geological Survey contracted Hi-Seis to acquire and process 20 seconds worth of reflection data, which equates to roughly 60 kilometres depth. We acquired this seismic along existing roads, some of which have lots of traffic, so lots of acoustic noise, which we don't want. So here in the right photo, it's not just a lovely picture of a beach on my holiday, it's the westernmost end of the southern line near Hamlin Pool. So you can imagine at daytime, there's a lot of tourists in that area. And in the middle there is one of the highways near Geraldton. So that's why some of the acquisition took place at night to minimise that noise that we'd get from traffic. And generally, the geophones are placed on the road verge alongside the route of the trucks. But as you can see here in Mount Magnet, they had to get a bit creative with where they planted those geophones, because on the other side of that median strip was footpath, so you really need to put the geophones in earth. So as you saw from Rob's talk this morning, there's a lot of existing petroleum industry seismic in the Perth Basin. It's a very mature basin for petroleum exploration. So that's what all these purple lines here are. So our interp has to tie in with these intersecting seismic lines and also be constrained by formation tops in petroleum wells and drill holes. And those formation tops must be constrained by biostratigraphy so that we know the age of the layers that we're interpreting in the seismic. But there's still a lot of challenges to this particular seismic interp project. Like any project, we have poor signal penetration in areas, and there's a lot of ambiguity as to where the top basement pick and where certain faults are. So you've seen a similar slide before in Fauna's talk. Here is the processed result of all three lines, all centred on the Darling Fault, which is where the arrow is, with the Perth Basin to the west of the arrow. So as I mentioned before, this seismic method can image the density and velocity contrasts. And in our final processed image, that's these red or black stripes. And what these contrasts mean is something we need to interpret. And in basins, these usually are the interfaces between sediment layers with differing lithologies and compaction. The lack of reflections is also an important thing we have to try to account for. So for example, within the Craton, we have good reflectivity at moho depths. But as you head towards the Darling Fault, you can see that reflectivity really drops off and also drops off under the basin itself. And signal penetration below a deep basin is always difficult, and a definitive moho signal is hard to see, and we're trying to understand more about this. If we zoom into the northernmost line here, into the Perth Basin, this is line MW1, we can see the geometry of the Perth Basin here is essentially two half-grabens against the Darling Fault and the Urella Fault, which is a major splay of the Darling Fault. So these two images are exactly the same, just the bottom one is the interpreted section. And please also note that vertical exaggeration has been applied just to highlight the structural features. The little red line there that you can see, that is the only deep drill hole that we have in the entire area. Therefore, the interpretation below this is tentative. So that means we have over 3 kilometres of completely unknown stratigraphy here. As a geologist, I find that really, really exciting, and it's always really fun to speculate, and until someone drills it, we can just speculate until the cows come home. Focusing back onto the basement to the Perth Basin, we can see these steeply dipping reflectors, which we've interpreted as the Proterozoic Yilgarn Basin. In the west, we can see the Proterozoic Northampton Inlier, which displays strong easterly dipping reflections, which are consistent with the metamorphic fabrics mapped in outcrop. And if you remembered earlier, I mentioned that the separate terrains of the Proterozoic Pinjarra Orogen were amalgamated along large structures, and I think potentially the Urella Fault is perhaps one structure along which those two very separate terrains were amalgamated, and then it was later reused by the Perth Basin, I guess. Also, interestingly, there's another fairly major fault here which was not mapped before, and so that just shows the value of these data sets. Deep basement tapping faults are potentially important for exploring for hydrogen, so finding and mapping exactly where these deep faults are is really important. That particular fault was not visible in other data sets that we had. So heading further south now and looking at line MW2, again we see the deep sedimentary fill against the Darling and Urella faults, but here the Urella fault has controlled much more basin subsidence. In the east, there is a large uncertainty as to whether that basal package is entirely Perth Basin stratigraphy, or perhaps it includes parts of the Yilgarn Basin. And the reason for that is because the dips of the Yilgarn Basin in outcrop 50 kilometres north are in places subparallel to the Perth Basin. So there might not be a very strong difference in seismic character between the two basins. So for me, that's a little bit tentative for now, but that's potentially where magnetic modelling could help. In the centre of the basin, the new seismic has imaged much better a complex fold in the hanging wall of the Coomallo fault than previous existing seismic. And now we can see the phases, there's the existing seismic there. You can't interpret too much from that. That's an old, I think a dynamite line from the 70s. And now we can see the phases of syn depositional faulting within the structure in the new seismic. Heading further south again, looking at line SW1, again we see here the importance of the Darling Fault in controlling the sedimentation. The Urella Fault at this point has already linked back up with the Darling Fault, so we don't see that here. Those of you who have eagle eyes might notice that some of those faults in the centre have really strange geometries, and that's actually just because we've got bends in the line. So when you're interpreting seismic, you really have to consider it's a 3D problem. You have to think about how your interpretation would look in 3D space. So that's not really how that fault looks in reality. But what I really like about this line is that it shows the pronounced thickening of the upper Triassic to lower Cretaceous section towards the east, and that's actually recording the final major phase of movement on the Darling Fault before continental breakup and the formation of the Indian Ocean. In the west of the line at the Leeuwin Inlier, we can see some nice easterly dipping reflections there. And those reflectors generally are consistent with the dominant gneissic fabrics mapped from outcrop, but more detailed work is needed to correlate the reflections with mapped geology. Right, that was a bit of a whirlwind tour through the seismic sections, but we still have a lot of work to do. But I think the new lines have really helped us image some complex structures in the basin and have helped clarify the depth and character of the basement. And some of the future work we have planned is to do some gravity and magnetics modelling, and that will help where the top basement peak is ambiguous. And also, as you saw before, integrating this work with the passive seismic. Unfortunately, we weren't able to get a good MOHO signature in the active seismic, but as you can see in this line here, and this is hot off the press from what I understand, we potentially have a good MOHO signal from the passive seismic, and correlating basement subsidence with MOHO topography will help us understand basin formation processes. And we have, as you've seen, these lines are up on our posters, and so I encourage you to go have an interpretation yourself. Thank you.